Greetings, everybody. So here's a problem I'd like to show you about the ratio test. And the ratio test is something that we can use to tell if some infinite series converge or not. Okay, it doesn't work for every infinite series, but I would say it often works for infinite series that have factorials or exponents. But we'll see some variety, and this is just one kind of question. So the ratio test, it will be the objective and the main focus of this question, but I don't want you to forget what an infinite series is. So real quick, I want to try to look at this in a very basic way before I talk about the ratio test. So okay, what is an infinite series? Well, so we take this formula that you see here, we let k be 1, we calculate, we get the first term. Then we let k be 2, we calculate, we get the second term. We let k be 3, we calculate, we get the third term, and we add all those terms up, and that goes on forever. Now, to say if this series converges or not just means that if I were to add and add and add in the method I described, would it seem like the grand total never exceeds a certain point, even if I add forever? Okay? If that seems to be the case, or if that is the case, then we would say the series converges. Now, I thought, why not, in order to make this really seem like math, why not look at that real quick? So one way that I do that is I use Excel. The reason is because Excel is widely available and used for lots of different things. You could do the same kind of experiment many other ways, but here I used Excel, and there's the Excel notation for that particular series to calculate the first term, which is about 0.05, the second term, which is about 0.18, and so on, third, fourth, fifth. And I just was curious. If I add the first 5 terms versus the first 10 terms versus the first 20 terms, what seems to happen as I add more and more numbers? And what I'm seeing here is that as I add more and more terms, the grand total really doesn't change that much. Okay, it really seems to level off at about 0.08. So I would get 2 impressions from this. One, it looks like the series converges because the more terms I add, the more the grand total seems to hit a wall. Like it's not going to get past 0.08 even if I keep going. That's the way it seems. Okay, and 2, it converges to probably something close to that number, 0.08. Now, okay, that doesn't prove anything, but I just show you this first because I don't want you to get so lost in the details of these theorems and tests and all the math that goes along with that to forget what is actually happening with the series. This is what's happening to it. We're adding a bunch of numbers forever and ever, trying to see what happens when we do that. Okay. The reason this doesn't prove anything is because this series does go on to forever and nobody can see that far. All right. But nonetheless, I think it does converge. Okay, so let's talk about how we use the ratio test. Here's the ratio test right here. A sub k is this formula, whatever it is, that gives us the terms of our series. And we can establish the ratio test by evaluating this limit. The limit is k goes to infinity of absolute a sub k plus 1 over a k. Okay, now a k is this. What do you think a sub k plus 1 is? That's what you would get if instead of a k in that formula, you put k plus 1. All right, so we'll set up and evaluate that limit. And depending on what we get, we have 3 cases to try to make a conclusion about. All right, so let's look at that. Here's our series. Question is, does it converge or diverge using the ratio test? Here's a k, and I have to calculate that limit, right? Step 1, I think, is just in reducing this. Like, let's not even worry about the limit because there's so much that I think has to be done to write this down and reduce it that to mix the limit in at first, I think it's just too much. So I'm going to take this absolute value, a sub k plus 1 over a sub k. And I'll get this. Do you see how I get that as my first step? So I put k plus 1 instead of k. I get k plus 1 factorial squared. I put k plus 1 right there. I get 9 times 2 times k plus 1 factorial on that. And over here, why am I multiplying? Doesn't this say to divide? Doesn't it say to take a sub k plus 1 and divide by ak? Why am I multiplying? Well, I'm multiplying by the reciprocal. Isn't division of this fraction multiplying by the reciprocal? So there is the reciprocal of ak. All right, so there it is. That's my first step, just to write that down. Next thing you might notice is, why is there no absolute value? I mean, the test says to have absolute value. Why don't I have that? Well, because there's no way that any of this could be negative. So I don't need the absolute value. Okay. So from here, I think we need to reduce this. So I'll do a few different things. I'll interpret this square right here. What is k plus 1 factorial square? Well, to square anything means you multiply it by itself. So I get k plus 1 factorial times k plus 1 factorial. Down here, you see this 2 times k plus 1 factorial? I think it would be best, for the sake of reducing this, to distribute the 2 on the k plus 1 to get 2k plus 2 factorial. Okay, and then I'll leave this 9 2k factorial alone. And again, this is k factorial squared. Well, to square anything is to multiply by itself, so it's k factorial times k factorial. Now, from here, here's what I anticipate happening. Like things are going to reduce out of this. So I'm going to just do a little rearranging. You know, these fractions are multiplied, so I can move things around if I want to. It's not going to change the answer. So like I can put the 2k plus 1 factorials, I can put those right above those k factorials. So just scoot those over there, because those things are going to interact with each other. Like the k plus 1 factorial is not going to cancel with the 9. All right, so I don't really see the point in writing them together. I think it'd be a little more obvious as possible if I wrote these things together. Then I'll put the 9 on top, move this 9 under it, and move this 2k plus 2 factorial under 2k factorial, because I think those are going to reduce. Now let's pause for a second. I want to make specific mention of how all of this cancels. And I think what I need to do is maybe review a little bit about factorials, because this formula here for this series has factorials in it. And I've mentioned them a lot going through this so far, but I haven't really told you what a factorial is. I've just assumed it at this point, but I think it's something worth reviewing. So for example, what is 4 factorial? Well, the way we calculate a factorial is we'll multiply from that number given as is down consecutively by 1 until we get to 1. So 4 times 3 times 2 times 1 turns out to be 24 in this case. That's how all factorials are done. Okay. What about n factorial? Like you might say, okay, if you have 4, I understand 4, 3, 2, 1, multiply, but what about some number you don't know, like n or 2k? That's kind of like what we have over here. It's not given what k is. All we know is that k is going to infinity, and that doesn't really help us reduce it. So I would say, well, the same principle holds. So in factorial, I don't know what the number n is, but it must work the same. So it's n, and then what's the number that's 1 less than n? N minus 1, and what's the number 1 less than that? N minus 2, so on and so forth, down to 1. Now I can't write this any more specifically than that, but that will be good enough right there. Okay. What about 2k factorial? Same idea. Start with 2k. What's 1 less than 2k? Kind of like how 3 is 1 less than 4. Well, 2k take away 1. And what's 1 less than that? 2k take away 2. And 1 less than that, 2k take away 3, all the way down to 1. Okay. What if you have factorials on top, like and bottom? Maybe to cancel. You could write them out like this. 6 factorial, 6, 5, 4, 3, 2, 1. 4 factorial, 4, 3, 2, 1. Do you see how there's this sequence of numbers that cancel? If you have 6 factorial over 4 factorial. Yeah, it's like from 4 down cancels out of both of them. Can you see that? Leaving you with just 6 and 5 in this case. Now that all together is what we're dealing with over here. So I plan to reduce this at this point. You see this part right here? But let me look at things individual. I want to look at how how does k plus 1 factorial reduce with k factorial? I'll look at that on its own. And how does 2k factorial reduce with 2k plus 2 factorial? So let's look at those. Here we go. So to figure out how these might cancel, I will write them out the way that I did up here. K plus 1 factorial, k plus 1, k minus 1, k minus 2, down to 1, k factorial, k minus 1, k minus 2, k minus 3, down to 1. Look how this sequence of terms match up exactly, leaving me this. It's k plus 1. If you see this over here somewhere, it's going to cancel to that and make it a lot simpler. What about this one? 2k factorial over 2k plus 2. Well, I'll write it out, and then I see from here down cancels out of both of them, leaving me what? A 1 on top, because every factor cancels up there, and 2k plus 2, 2k plus 1 on the bottom. So that's how these are going to cancel. See? All right. Now, with that being said, here's what I get. This k plus 1 over k factorial cancels to be k plus 1, like that. But this other pair also cancels the same way. And I guess if you had to say there was something under it left over, it would be 1. The 9s cancel, and 2k factorial over 2k plus 2 factorial reduce like that, leave me 1 over 2k plus 2, 2k plus 1. So to get from here to here is all right there. Now, with the aim of simplifying a little more, I'll just multiply these things together. I get what you see here. Okay, now that's the algebra. That's taking what the ratio test says we have to work with and reducing it to some point where I think we could then apply the limit. But I didn't want to do that all in one step. Okay, so now I'll apply that limit. Here's what I get reduced from the ratio test. So now I got limit k goes to infinity, k squared plus 2k plus 1 over 4k squared plus 6k plus 2. That is an indeterminate form of infinity over infinity. We use L'Hopital's rule to do that limit. I wasn't going to show that in this video as to not give you too many details, but if L'Hopital's rule or how this limit is done in general is something you get stuck with, then please reach out and we can talk about it. So it's 1/4, okay? So do you see this objective of the ratio test? The end result of calculating that limit? It turns out it's 1/4, okay? Now, what does that say? Let's go back and consult this. So with the ratio test, our objective is to calculate that limit. We get some number r. If r is less than 1, we're in case 1. If r is more than 1, case 2. If r is 1, case 3. We got 1/4, so we're in case 1, and it means the series converges absolutely, which means that the series as it is converges, okay? So, all right, my conclusion, it converges absolutely by case 1 of the ratio test. So there are a selection for an answer, at least on my math lab, fits into B. It converges absolutely because we got R, that limit from the ratio test, to be 1/4. Now, we can't be too surprised about that. Our final statement, it converges. I thought it looked that way when I played around with the series a little bit. I thought it looked like it converged because as I added more and more terms of the series, it seems like my grand total can't exceed about 0.8. That's what I would expect it to look like if it did converge. Okay. Now, one other thing, we're not saying the series converges to 1/4. Okay. 1/4 is just this identifying number to use the ratio test. Okay, and figure out which case we're in. I'm not saying this series is such that if you add more and more of the terms, you'll get 1/4, because that's obviously not what happens. All right, so we can say it converges by the ratio test. The ratio test alone doesn't tell us what to. This number is not involved in that final statement about whether it converges or not.